Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 2.3, part 2 on inverse linear transformations. We'll go over the formula for finding an inverse linear transformation and walk through some example problems to see if an inverse linear transformation exists, and if it does, what it does geometrically to a vector. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. We'll begin by learning how an invertible linear transformation is defined. A linear transformation T from Rn to Rn, defined by T of x is equal to A times x, is invertible if it is both 1-to-1 and onto. A transformation is going to be 1-to-1 and onto when matrix A is invertible. This inverse linear transformation is defined and written as T inverse of x is equal to A inverse times x. When we multiply a vector x by matrix A, vector x is transformed into vector T of x. T of x is A times x. T inverse of x, as we saw defined above, is equal to A inverse times x. When we take the inverse transformation of the transformation of x, we get T inverse, and then for T of x, we're going to substitute in A times x. And this is equal to, following this definition up above, A inverse times A times x. And this is just equal to x. This is shown in our graph that when we multiply AX times A inverse, we get back vector x. Let's now look at an example where we're given that T is a linear transformation from R2 to R2. We're asked to show that T is invertible and find a formula for T inverse. Our transformation that we're given is listed here. If our transformation is invertible, A inverse will exist. So the first step that we have to follow is to find A inverse. Let's first write down what A is. Reading off of our transformation up above, our A is equal to 4 minus 7, and then minus 5, 9. A inverse is 1 divided by the determinant of A, and that's the main diagonal elements multiplied, which gives us a 36, minus the off diagonal elements multiplied, which gives us a minus 35. We then have the matrix 9, 4. Remember, the main diagonal elements get switched, and then the off diagonal elements get a negative applied to them. This gives us that A inverse is 9, 7, 5, 4. Now we can complete our second step. The second step is to find T inverse. To do that, let's write down our formula. T inverse of x is just going to be A inverse times x. This is equal to 9, 7, 5, 4. And then our x, following our transformation written above, is x1, x2. And this gives us an answer of 9x1 plus 7x2 in the first row, and 5x1 plus 4x2 in the second row. Let's put our answer in the same form that the original transformation came in. This gives an answer of 9x1 plus 7x2, and then 5x1 plus 4x2. Let's now look at some invertible geometric linear transformations in R2. In section 1.9, part 2, we studied geometric linear transformations that reflected, projected, contracted, expanded, and sheared vectors in R2. Some of these linear transformations that we looked at are invertible, and some are not. Let's now look at some examples and determine if the linear transformation given by matrix A is invertible, and if it is, we're asked to describe what the linear and inverse linear transformation does to a vector in R2. To determine if the linear transformation is invertible, we'll begin by finding A inverse. A inverse in this example is 1 divided by 4. The main diagonal elements switch, and the off-diagonal elements are going to stay the same because they're 0. This gives us a matrix 1, 0, 0, 1 quarter. Since our A inverse exists, we know that T is invertible, and T inverse exists. Let's now see what the linear transformation does to a vector x. We have T of x is equal to A times x, and we're going to take our original matrix A, 1, 0, 0, 4, and multiply it by x, which we'll write as xy. This gives us our first component is x, and our second component is 4y. This transformation stretches vectors vertically by a factor of 4. Let's now see what our inverse linear transformation does to a vector x. We have T inverse of x is equal to A inverse times x. Our A inverse we just found, it's 1, 0, 0, 1 quarter. We're going to multiply that by xy, and we get the vector x 1 quarter y. This transformation shrinks vectors vertically by a factor of 1 quarter. We can understand this better graphically if we make a diagram and we let vector x be equal to the vector 1, 1. The transformation of vector 1, 1 is just our matrix A, 1, 0, 0, 4, times 1, 1, and we get the vector 1, 4. Let's go ahead and graph that. You can see that it stretches vector x vertically by a factor of 4. Let's now look at what the inverse transformation does to our T of x, which we just found to be 1, 4. We take our A inverse, which is 1, 0, 0, 1 quarter, and we multiply it by our T of x, which is 1, 4, and we end up with the vector 1, 1. Let's graph that. Our inverse linear transformation maps the transformed vector back to the original vector. Let's now look at our second example. When we look at matrix A, we notice that we have a column without a pivot. That means that we do not have 2 pivots, and that tells us that A is not invertible. Since A is not invertible, we won't have an inverse linear transformation. Let's find T of x to see if we can understand graphically why the inverse linear transformation doesn't exist. Our T of x is equal to A times x, and that's 1, 0, 0, 0 times xy, and that gives us the vector x, 0. This linear transformation projects vectors onto the x-axis. When we project vectors onto the x-axis, we're reducing a 2-dimensional space to a 1-dimensional space. When this happens, the transformation cannot be reversed to recover the original 2-dimensional coordinates. Be sure to check out the next video in this series where you'll learn all about determinants. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.